Hello students, welcome back. Let's go to section 2, some linear algebra of linear ODEs. We have variable coefficients, but most of the things that we went through will just stay true. And here's one. The operator L is linear, which means you have to prove that it preserves the linear combination. What is the operator L? Well, here it is. This was for linear ODE with constant coefficients, where all those coefficient function, an minus 1, all those are constants. Now this is the one. Here this time, an minus 1, all those are expressions of t. So you have variable coefficients, but still you can prove this operator L is linear. How do you prove it? Well, here, these coefficients are expressions of t, but these coefficients, C1 and C2, those are constants. That's why it works out. So if you put something inside, you're taking constant coefficients. Here, the operator L includes variable coefficients, but inside, when you take the linear combination, these are constant coefficients. That's why it works out. Exactly how? That's left to the students. Same as before, technically exactly the same actually. I want you to just redo it. How about this? The solution set of the homogeneous equation L of y equal to 0 is a linear space. What do you mean by that? It's closed under linear combination. So y1 and y2 are solution, then cy1 plus cy2 is also a solution. So how do you prove it? Again, you can use the linearity property of this operator L, and please note that C1 and C2, those are constants. You see, here in the definition of L, we have variable coefficients, but inside, we consider constant coefficients. So there's a subtle difference between one and the other. When you deal with linear ODEs with variable coefficients, we consider variable coefficients to the operator and the equation itself, not the linear combinations of the solution. Those are constant coefficients. I cannot emphasize that too much. I repeated the same thing already 3-4 times, I guess. Now, next topic I'd like to review is linear independence. Everybody should remember that, of course. What do you mean by linearly independent? Take the linear combination, and if that's constantly 0, that means only one thing. All the coefficients are all 0. Otherwise, we call it linearly dependent, which means not all of them has to be 0, yet the linear combination will turn out to be constantly 0. So for example, maybe 2 of them are non-zero, maybe 5 of them are non-zero, or maybe all 17 of them are non-zero. Whatever it is, linear combination is always 0. In this case, whenever a linear combination is constantly 0, all coefficients, all 105 of them, all of them is 0. So that's the difference, linear independence versus dependence. Now, what if you have just a pair of functions? And that's typical because most of the real example that we are going to deal with here is going to be second order equation. And the second order equation will give you only a pair of functions, just 2 functions. And it's going to be a lot easier to check because we don't really have to check the entire definition and all the linear combination. Just check the collinearity. See if one function is just constant times the other. As for the proof, we already went through it, so I'll just move on. For example, if you want to check if these 2 functions, cosine of t and sine of t, are linearly independent or not, you can put those into the, to the definition and take this linear combination constantly equal to 0 and plug in some t's and then solve the system of linear equations. Okay, not too bad, but it's tedious. A lot easier way is check if one function is constant times another. They're different. clearly they are different. If you take the ratio, you have sine of a cosine, which is tangent, not constant. So collinearity is very useful. Now, one more topic here is Ronskian or Ronskian. Ronskian is a determinant given by this square matrix obtained by y1, y1 prime, and y1 double prime all the way over to n minus first derivative. So original 0, first, second, third, all the way over to n minus 1. So there are n rows here. Same goes to the second function. Same goes to the nth function. So we have n by n matrix here, square matrix, and that determinant is called the Ronskian. The Ronskian determinant is 0. That means linear independent. Non-zero means linear independent. It turns out Ronskian is constantly 0 or never 0. If it hits the x-axis several times and sometimes 0, sometimes non-zero, then something is wrong. Most likely your computation is wrong, or maybe y1, y2, those are not the functions, or you may be operating outside the interval of definition. All kind of hell can break loose. But of course, most likely that you made some calculation mistake. It turns out Ronskian is constantly 0 or never 0. And as for the proof, yes, we'll prove it. It's hard, but we'll prove it. We're going to do it in an optional video. Most of the time, however, we're going to deal with only the second order. So we don't have this big determinant. 99% of the time, or maybe close to 100% of the time, if we count the actual problem that you have to get your hands dirty, then it's going to be order 2 only. So you have to have just second order determinant. And that's easy. And just multiply the principal diagonal, y1, y2 prime, and then subtract the other diagonal, y2, y1 prime. So you can remember this as the formula for Ronskian. Is it useful? To a certain degree. We will not use this to check the linear independence because we have much better tool, collinearity. But there are some other uses of Ronskian. Let's come back here. We know these two are linearly independent because they are not collinear. One is not constant times the other. But what if you want to check using Ronskian? Well, here we go. Determinant of y1 and y1 prime, y2 and y2 prime, and calculate the determinant. We have cosine squared plus sine squared, so it's constantly 1, which is never equal to 0. How about this? We have a little bit more difficult determinant computation here. I take it back. Determinant computation is not difficult. Derivative computation can be a little bit hard because we have product rule and chain rule here, which corresponds to that. But then again, the determinant computation is not too bad. Multiply the principal diagonal and then subtract the other diagonal and simplify. You're going to get e to the 6t, and that's never equal to 0. Exponential is never 0. A bit of an overkilling, isn't it? It's clear that one function is not constant times the other, so collinearity is a much easier way to check the linear independence. But do not completely disregard Ronskian. We're going to come back and use it in Module 10. Okay, that's where I'm going to stop. We're going to go to Module 3. We are going to go over to Section 3 of this notebook in the next video.